One of the most important statistical models that was ever made in the 20th century was the analysis of variance. And what it did, it unleashed the power of the scientific experiment onto the world for better or worse. The breakthrough that Fisher created with this statistical model was that you could compare the performance of several groups. What does that mean? Well, if you have plants that grow and if you add fertilizer, different types of fertilizer, then you can compare whether there is a difference among the fertilizers and which fertilizer works best. So that's the great breakthrough of the analysis of variance. And how it does that is it compares the within variance of the model with the between variance. So that's the important thing. All the variance within the individual group is set in relation to the variance across all the groups. So between, like within the groups, between the groups, that is being compared. And that's the most important thing, that you then ultimately can know which group works best, which one works worst in terms of like how they increase agricultural yield in terms of fertilizer. Well, and what is tricky then is that you can also know how much the model explains. You not only get p-values, you not only get the significance, so in other words, whether there's a significant difference among all the groups, but what's more important is you also get the explained variance. So you know how much the different factors together explain. And that is something that is very valuable, because then you know whether you have a strong or weak effect. Since this is all built on the normal distribution, you have to check this out again. So that's a really important point, that you look at a histogram across the different levels. Some people say of the raw data, some people say again across the residuals of the model. So, but what is relevant is that whatever you have, you report. And if your sample isn't good enough, you will see it in the histogram. Maybe you can't change anything about it, but at least you can give some confidence to your result. And you can say whether it works better or worse. But what now is kind of like the problem that came with the analysis of variance is that people started to look increasingly through a world of categories, through a world of factor levels. So this lens of dividing everything into more or less or different quantities or all sorts of groupings took the quantitative continua somewhat away from the world. So of course regression might be the most important model that we have, but the scientific experiment is really there to stay. Without it, we wouldn't be able to compare the effect of vaccines, we wouldn't be able to compare the effects of different drugs, we wouldn't be able to make psychological or ecological experiments, and now even people in the economics use it and lately won a Nobel Prize for it. So the analysis of variance is here to stay. It's a little bit simplistic today, and it's being replaced increasingly by more complicated models such as mixed effect models. But what is relevant is that in order to be able to apply these, you still need the knowledge about the analysis of variance as a baseline. You still need to understand how this actually came to be and how you design your studies. A study design is something that you learn step by step. You start with the more simple one, and then you increasingly become more and more complicated. So that's something that takes a long learning curve. And being able to make modern, say, medical designs is really the gold standard of scientific research when it comes to experiments. So, and that's something that we need to remember. The analysis of variance is always a stepping stone in our learning, and then we can go deeper into more complicated models.